Good morning, friends. I feel immense pleasure to be here for my course, Engineering Thermodynamics. I am in the second module. The second module, it is starting with the second law of thermodynamics. In second law of thermodynamics, we have discussed that two statements. We also have discussed about corollaries, equivalent of Kelvin-Planck statement and the Clausius statement. We have also discussed about the Maxwell demons. We have also studied about the perpetual motion machine of second kind, Maxwell demons, reversible processes, irreversible process, factor affecting irreversibility. These topics I have covered in my last lecture. In today's lecture, I am going to take about Carnot cycle, an example of reversible cycle. Carnot cycle for control volume or a flow system. Carnot theorem, then corollaries, then how to find absolute temperature from second law of thermodynamics. This I am going to discuss in today's lecture, and really it is very wonderful and very interesting topic, because we have seen that the second law of thermodynamics will give the direction of your energy flow, and the efficiency of any cycle, it cannot be, this eta is equal to 1 minus QL by QH for a given temperature zone. The Carnot has designed one very hypothetical cycle, and he has explained that the maximum efficiency which we can get is not more than this cycle, and till now nobody has got more than that. If any one of you are very good researchers, you can find out some ways and means, so how to get the reversible cycles where the losses are zero, then our engineers can make very nice engines, gas turbines, your thermal power plant. These all concepts are used in those thermodynamic area where we convert heat to the work to the heat. These all processes are used in those type of systems. We have discussed about the perpetual motion machine, those machines which are hypothetical. We should not waste our time to doing such type of activities. Maxwell demon, this is like a robo, it is in the gate, and for the high temperature molecules to the low temperature molecules, how it can separate. Reversible processes, and we have also seen the irreversible process, how the reversible will happen, and the irreversibility, the friction and the free expansion, the mixing of the gases. These are the factors which are affecting the irreversibility processes. Now I will discuss about the Carnot cycle, an example of reversible cycle. This is one of the example. It doesn't mean that only Carnot cycle is only the reversible cycle. There is erection cycle and some other cycles are there. They are also reversible cycle, but the result is same. What the Carnot has got, other people also has got, but different processes are somewhat different. So what is that Carnot cycle and how this can be a reversible cycle? Let us say we have a piston and a cylinder arrangement as shown below. It compresses slowly with the insulation. So just you can see that this one is a piston here. This is the cylinder here. Okay. So in this process, some gas is here, and this is insulated, because insulated means heat will not go outside, heat will not come inside. There is a restriction of transfer of heat. This is happening due to the putting the insulation. So it is a reversible adiabatic compression. So first one is, it is reversible adiabatic compression. Now if we remove the insulation, first one is you are compressing. Now if you remove this insulation, transfer heat from source to system and expands slowly. So now here is the source. In the diagram, from here to here you have compressed. In this stage the piston has reached up to here. Now from the source you have to take some heat. This amount of heat is QH. Here you will have TH minus del TH. Means it is very minute, less than this. Otherwise it will not transfer, will not take place. We cannot write TH. Some of the books you will get the TH. But in fact we should keep here TH minus del TH. This del TH is extending towards the zero. Very small. Now if you remove this insulation, so heat will be transferred from here to here, and again it will reach to the new position here. In this new position, so it is called, this is a reversible isothermal heat addition. So this is the figure 2, is a reversible isothermal heat addition. Again put back the insulation and keep on expanding slowly. So now you put this insulation and keep on expanding. You remove the weight and it started expanding. This is a reversible adiabatic expansion. This is a reversible adiabatic expansion. Everywhere the gas is here. So now it is expanded. Last and the fourth one is again you put a sink, a cold zone. So this heat which you have got from here, it will be released here. So the temperature of this zone will be TL plus del TL. This del TL is extending to 0. Very small. So this is called reversible heat rejection. This is also isothermal, reversible isothermal heat rejection. This is a reversible isothermal heat addition. Okay, so like this we will get this process. So this is your Carnot cycle. We have the 4 processes. So if you want, I can draw I will draw the PV and the TS diagram. First I will draw the TS diagram. Okay, so this is the adiabatic, reversible adiabatic 1 and 2. Reversible adiabatic compression. 2 to 3 is reversible isothermal heat addition. 3 to 4 reversible adiabatic expansion. 4 to 1 is reversible isothermal heat rejection. Okay, so these are the 4 processes which we can see it. So we can write it like okay, so 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So this is the PV diagram of, it is not okay. So like this is the PV diagram for the Carnot cycle. Okay, so What is the Carnot cycle? Fluid operates with the temperature limits and does not work. If the fluid is operating between the given temperature TH and the TL, so the work will be done. Having all the processes are reversible with 2 reversible adiabatic and 2 reversible isothermal called the Carnot cycle. Just now I have shown here. The above discussion is for the control mass system, but we can also find the Carnot cycle for a flow system or a control volume system. So this is for the control mass system. Control mass system. Now we have to see that how this can work for a flow processes like turbine, compressor and other places we have the flow processes. So we will see that how in thermal power plant, how the gas turbine, how the compression and other things are working. So here we have the Carnot cycle for control volume or the flow processes. Here we will see how thermal power plant can be treated as flow system or a control volume system. Figure below depicts the processes. So this you can see that here we have the heat source. This is the source. From this source you will get the heat from here, and this heat will be given to the boiler here. In boiler some water is pumped from here. So this boiler will convert, due to this heat, the water will be converted to the steam. This steam is entering to the turbine. In turbine, this steam is expanded. Due to this expansion, the work is done and this start rotating. This is the turbine work. This start rotating. Due to this, the rotation of this is connected here with the, this is connected to, sorry, this is the compressor. It is connected here by the shaft. So it is also rotating. This will be, this work is given here by, it is called WC. This is the WT. So net work out is equal to WT minus WC. This is the work done by the system. So from here, water is supplied to the boiler, heat is supplied to the boiler. Due to the heat, the water is evaporated. This evaporated water will become the steam. This high temperature and the high pressure steam is entering to the turbine. Due to the expansion in the turbine, it start rotating. This rotation, some part is given to the compressor, so that compressor will also rotate. From this, exhaust of this turbine is given to the condenser. From the condenser, this is the a river or any heat rejection source, that is the, it is called sink, where heat is rejected. Heat is rejected. QL is rejected. QH is given. This is very, very important. You cannot make directly from here to here. Heat has to be rejected. Then only, otherwise it will become a perpetual motion machine. This type of machine is not possible by the second law of thermodynamics. It violates the second law of thermodynamics. So we should make some energy has to be discharged in a sink. So this low temperature and the low pressure is coming here. It is condensed. Steam is converted to the water and it is thrown to the sink. From here it goes to the compressor, because here pressure is very low. So this goes to the compressor. It will compress it and it will give to the boiler. Now I will discuss about the processes. If you see here, the first process which we have seen is a adiabatic compression. So reversible adiabatic compression is happening in the compressor 1 to 2. 2 to 3, 3 to 4. Okay. So here if you see 1 to 2 is adiabatic, reversible adiabatic compression. In this compression and the turbine, your heat should not transfer. 1 to 2 and 3 to 4, heat should remain there only. Now from 2 to 3, heat is added, adiabatic, reversible adiabatic heat addition. This heat is added by the fuel or coal or petrol or gas, anything we supply from here, and this is heating the boiler, and this water is entering from here, and this is heated, and from here 3 to 4 is your reversible adiabatic process, that is called expansion, and the work is out. Okay. From here 4 to 1, it is reversible isothermal heat rejection. So all the 4 processes of Carnot cycle for a control volume or the flow system is also explained, and in this way you can find out the same 4 processes as for the control volume. You can also write for the control volume system like a control mass system. Now I will discuss about Carnot cycle, Carnot theorem. This theorem is state that working between the same temperature limits, efficiency of any reversible cycle is less than the corresponding value of a reversible cycle. So if you are working in the same temperature limit TH and the TL, the efficiency of an irreversible cycle will always be less than the corresponding reversible cycle. That is the theorem of Carnot. Let us assume that here we have this diagram that eta irreversible is greater than eta reversible. That is our assumption. Whether it is true or not, operating between the same temperatures, that is TH and TL. These are the temperature limits. So here first we will see the heat engine, and here is the heat pump here. So we can see that from heat engine it is a source is TH, and from here it is taking heat QH. It is an irreversible cycle. So this is the heat engine, and from here QL is rejected in the temperature TL. From here some work is taken from here, and this work is given to the reversible cycle. This is here the reversible cycle. In the reversible cycle, QH and Q prime L, this I have added here in the same zone, TH and the TL. So now this is the reversible, and here is a irreversible. So whether it is working or not, that I want to justify. So we know that we have taken assumption that eta, the efficiency of irreversible cycle is greater than eta of the reversible cycle, means the work done, this work done of this irreversible cycle is more. Work done of the irreversible cycle is more than the work done of a reversible cycle, is equal to, it is work, net work. So net work will be W irreversible minus W reversible. Getting net output, but heat source is same, but exchange of heat with a single reservoir. Just you can see here, we are taking here also QL, you are taking from here, and again you are here, it is coming. It is not possible, because the Kelvin and the Planck statement says that, so the assumption we made, that is eta irreversible is greater than eta reversible, is not correct. So eta irreversible means the efficiency of an irreversible cycle will be less than the efficiency of the reversible cycle. That is the called Carnot theorem. That it is proved that this is the Carnot cycle, and it is working in this way. Now I will discuss the corollary 2 of the this second law of thermodynamics again. Operating between the same temperature, all reversible cycle have the same efficiency. So another way how we can express that, like reversible cycle efficiency will be always more than the irreversible cycle. Same way, the reversible cycle will have the same efficiency in the same temperature range. So major conclusion, efficiency of the reversible cycle is a function of the temperature. So the efficiency eta is equal to 1 minus QL by QH. It is a function of the TL and the TH only for the reversible cycle. So here we can write QL by QH is a function of TL, TH for the reversible cycle. To understand, we form a hypothetical setup. So we will see that for the reversible cycle, QL by QH is a function of TL by TH. So in this way, we will find out the absolute temperature here. Here in this way, we are able to find out the absolute temperature, and this is obtained from the second law of thermodynamics. Here we can see that source is T1, heat is taken as a Q1, work of a reversible cycle W1, this is the heat engine 1. From here it is heat is rejected Q2 to the sink T2. From here it is going to the, again here Q2, going to the Q3 to the temperature of sink T3. Work is here done, W2 reversible, here it is W1 reversible. Another system, we will have only one, that is, we are taking the Q1 reversible heat engine, work is done is equal to W3, and this is the Q3, and here is the T3. So just we will see that both it is, we are able to find out something new property, and that is called the absolute temperature. So we have seen the previous one that Q1 by Q2 is a function of T1 and T2, and the Q2 by Q3 is a function of T2 and the T3. This is all only for reversible cycle, reversible processes. Okay, and Q1 by Q3 is a function of T1 into T3. Now we can write that Q1 by Q3 is equal to Q1 by Q2 into Q2 by Q3. Now we will put this function here. F T1 into comma T3 is a function of T1 T2 into F T2 T3. If we see in the right hand side, we don't have the T2. So we have to remove this T2 from the right hand side. So how to do? So we will write F T1 T2 is equal to G T1 by G T2. G is another function, and so G T1 by G T3 is equal to, we can write here G T1 by G T2 into G T2 by G T3. This T2 and T2 is out. So we will be having G T1 by G T3. So we got here that Q1 is equal to QL by QH is equal to G TL by TH for reversible cycle only. Only taking the linear form, so GT is equal to T. GT we can write as only T. So QL by QH is equal to TL by TH. This defines the absolute temperature, which is not dependent on the volume of substance. From here we got the absolute temperature. So absolute temperature we got QL by QH is equal to TL by TH, and this gives absolute temperature scale. In 1944, In 1954, temperature of the water of the triple point was found 273.16 Kelvin. This is called 0.01 degree centigrade. Given name of honor to the Lord Kelvin, that is K is equal to 273.16 Kelvin. Difference between Kelvin and the degree centigrade is same. Absolute temperature scale with heat transfer was given by equation 1 here. So here absolute temperature scale with the heat transfer was given by equation 1 above. So it is called the absolute temperature, as TH was not dependent upon the volumetric expansion. So this TH, TL not depend on the substance volume. Okay, so from here we got one more new property, that is called the absolute temperature scale, and this is the result of second law of thermodynamics, and we got that the triple point of the water is 273.16 Kelvin or 0.01 degree centigrade, and this K is called 273.16. So that much we have to add on the degree centigrade. So in the next class, this is the next class. So in the next class, we are going to discuss about Clausius inequality, Clausius inequality in other form, entropy, TS diagram, and efficiency of Carnot cycle. These things we will be going to discuss in our next class. Please be tuned for that. These are the references. These references are taken from P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition, Eunice Sengel and Michael A. Bowles, Thermodynamics and Engineering Approach, and NPTEL lecture by the Dr. Mishra, IIT Kanpur. If any questions, you are welcome to ask. Also, I request you to like and subscribe. If you have any problem, you can give in comment box in this channel. Also, you can mail me in this mail ID @gmail.com. So this you are welcome to do this, and hope you learn something and it is quite good. Thank you very much for joining this class. Please be tuned for my next class. Very soon my next lecture is also coming. Thank you very much for joining.
Like, share and subscribe. Hit the bell icon for more updates.